angular to tangential. Ready?
I started already.
You already started. Okay, cool. All right, so rotations, like I said before, in some ways everything we've done for many of you is for the purpose of being able to analyze rotations and certainly oscillations too. If you want to know light, you want to know quantum mechanics, you want to know electric circuits, all that stuff comes into rotations, and oscillations are key. And the nice thing is we can build this framework. So when I talk about rotations, we're going to see that I can talk about things that are going around in a circle or things that are spinning like this. So there's kind of two ways that we can talk about it. And we've talked about uniform circular motion, something going around in a circle at the same speed, staying at the same radius. And you can have things spiraling in, changing speed, all kinds of crazy stuff, but we're not going to get there in this class as an introduction. So there's the spinning around its own axis, and then there's the rotating here. And it applies in astronomy. It applies to huge galaxies with billions of stars and things going on to it. It applies to mechanical systems here. If I go like this and there's so many rotations happening all in here. So if you want to engineer this, it's like what radius, how fast, how are you going to make that work? We'll talk about torque later. You go in here and this thing spins, and then there's a belt here, and you got this axis of rotation spinning, and this spins over here, and then I got this over here, and I got this circle, and that circle, and that circle, and it's just crazy circles, and it's fun, but you can learn it. A lot of learning, remind you, is really about familiarity, and so you have to just put in the time, and that's why the homework is so good, to get familiar with the stuff, and eventually it starts getting easier. You can do all kinds of cool things with this. You can, again, here's an electric motor. So that rotates, and then I can make this thing rotate. And then it spins this way, and then it rotates around that way, and stuff happens. So we want to be able to describe all this stuff. And look around you. Your body is all rotations, muscles and bones. So our first task is to describe the kinematics, describe the motion. So let's go up over here and just quick reminder. Kinematics describes the motion. It doesn't say why things move the way they do. That's Newton's laws, where we have the concepts of inertia and the concepts of interaction. Force will turn into torque, we see. So we're going to measure time, and in today's lab we're going to measure time and displacement. We analyze it by looking at time at instants, and a good notation works really well, or an interval of time. So it's helpful, again, sometimes people just use t and they mean delta t, so be careful with that. Space, we can have positions, we can have displacement, and we can also have distance. Know the difference between those concepts. It's not too bad. We have rate of travel. So the rate of travel at an instant or over an average period of time or at an instant. And we can have acceleration. That's the rate at which the speed or direction changes at an instant or average. Okay, cool. Questions? We'll be fine with that. That's all we're doing. And so this has a chance to become easy pretty quickly if you've been doing your kinematics and homework and all that stuff. Rotational kinematics, we can talk about an object going around in a circle, so I can spin something like that, however we do that, spin something around in a circle like that. We've done all that force analysis on that. And I can talk about something spinning around its own axis. And by axis of rotation then, that would mean the axis of rotation would be which way? Which way is the axis of rotation of this? The axis of rotation.
Pointing up.
Pointing up or down, whichever way you do it. The axis is like an axle. This is the axis of rotation, and here's the rotation. So that's going to be a very useful thing for us. And as you know, we want to do these analyses using careful notation in a way that takes us to places that our intuition might not. It might surprise us or it might validate us. We'll see. So axis of rotation is like this. If I go like this, this is spinning around like this. The axis of rotation would be up and down, like an axle. Is that clear? Is that good? Yeah? So then I can draw that this way. In fact, I'm going to use a distinction for an axis of rotation. What does a dot with a circle mean? Which direction is that? In or out? Remember for vectors?
In.
That means
It's in.
out. And that means, oops, out. And that means in. So we're going to use, because most human beings are right-handed, I'm going to introduce this idea. It gets a little abstract. So we're not going to go there right yet. But let me introduce it. Because most humans are right-handed, sorry lefties, it actually works out well for lefties because they get to write with their left hand and use the right hand over here. Right-handers have to put their pen down. If I'm moving this way, we're going to see later, this is just a preview, that I would call the direction out. If I'm moving this way, I would make that in. If this is spinning that way, I would say it's going out, spinning that way in. It's just going to be a bookkeeping device. So don't worry so much about that. Just forget I even said it. We're going to come back to that. So I can have these two cases to talk about the rotations. Those two kind of different cases. So you can think about these and analyze them in terms of three different ways that are totally connected. And you just have to decide which way you want. So again, initially, if you're trying to memorize everything in a disconnected way, it's overwhelming. But if you see how they're connected, it's not hard. You can talk about the revolutions, the angles. Radians always work. You can use degrees, but you'd have to convert radians, or tangential components. And so right now I'm going to do revolutions related to angles, then I'll do angles related to tangential. So over here, let's talk about this kind of quickly. Revolutions versus angles. So for displacement, sometimes we'll use n, people use different things, for the number of revolutions, how many times around. It could be a fraction, it could be more than one, whatever. And for displacement in terms of angles, often books will just write theta when they mean a change in theta. How far around have you gone? And so what's the connection between these two? If I have n, how do I get delta theta? Or if I have delta theta, how do I get n? This is the critical thing in analyzing rotations, and that is the following. So let's go over here. This picture here is really essential. If an object goes around here, and we're keeping the same radius, of course it can get more complicated than that. It travels a distance. Often the arc length can be s or l along that length. This is delta theta. And so we're going to use this connection a lot. If I go around once, I'm going to have one revolution. Now watch out here, I'm going to fool you. Is equal to how many radians? 2 pi radians. Ready? Hold on. They're not equal. It's not the same thing. So don't use equal unless you mean equal. Okay? They're not the same thing. You have to convert. It's true that one revolution physically will give you, but this is delta theta, and that is the revolution n. So they're not the same. But if you have one, you can get the other one. How do I do it? Well, let me see. If I have half a revolution, I have delta theta would equal how much? Quick.
Pi. 1 pi. 1 pi.
Pi radians. Come on, we got to can print this. If I go 4 revolutions, what's delta theta?
8.
8, right? 8. So how do I go from one to the other? How do I get delta theta if I know n? If n is 1, I multiply by 2 pi. If n is a half, I multiply by 2 pi. If n is 4, I multiply by 2 pi. Just because of that. So this is critical to have that not ever, be a worry. And if you want to go back and forth, well, if you want the number of revolutions and you have delta theta, of course, you divide by 2 pi. So that shouldn't be memorized, it should be understood very clearly. And if you can do that here, you can do that for all of these guys. So, any questions about that? If you just think about that, then I can write an equality. I can't say n is equal to delta theta. That's sloppy. Good? Yeah? Okay, so again, don't memorize it, think about it, realize, do these exercises, you're good. So 2 pi is the relationship here. Now, if I talk about the rate of travel, I can talk about the frequency. How frequently do I go around? Well, that is how many revolutions per second, or you'll see, often in the homework, revolutions per minute, or RPM. If we're using seconds, which we frequently do, we can use nanoseconds too. We can use microseconds. You can use anything you want, right? But we can use minutes just as well, or hours if it's slow, or days. So revolutions per second, revolutions per minute, you should be able to convert between those two, would be frequency. What is 1 over frequency? Period, right? That's the time. So that would be the seconds per revolution, the minutes per revolution. So recall that period, we use capital T often, is 1 over the frequency. And again, that's not really something to be memorized, just understand it, know it, certainly off the top. So in frequency, I can talk about the average frequency, which is the number of revolutions over time. And if frequency is constant, then that's what it is. It's always the average. If it's changing, well, then maybe it's slowing down or speeding up, and we often don't really go here. We usually use that right there. So, in terms of rate of going around, again, just rate at which I'm going around, I can talk about frequency, or I can talk about how many angles do I go around, how many radians do I go around per second or per minute or whatever you want. So that's omega, lowercase omega, not a W, don't say W, lowercase omega, rounded, not written like a W, in radians per second, that's all it is. So omega average would be the change in the angle over the change in time in radians per second, say. The omega at an instant, at any instant, would be d theta dt. Cool? That's just like velocity is in the x direction is dx dt, velocity y is dy dt. It's the same idea, but now we're talking about the rate at which it's going around. And again, the connection here is simply, since I'm going, really, I still have seconds, I'm just going from revs to radians, then it's just a 2 pi. If you think about it, you don't even have to, okay, let's see, omega then. Omega is equal to, that dt is 2 pi n dt. So 2 pi f, isn't it? Use units, study it, get used to it, then you'll act like it's just obvious, but be considerate of those learning it, because it's a lot of symbols. And so too, I can go, well, frequency is omega over 2 pi. Now, to make it even, again, if you're memorizing, you're sunk. What about t? Period, that's 1 over frequency. And so that means omega is 2 pi over t. Because that's one over frequency. Again, and t is equal to, flip that, and 2 pi over omega, right? You see it? And so, again, at this point, you want to make sure you're writing it on paper, because in your brain, you could easily get it flipped, and you don't want to do that. It's just too costly. Okay. So we can talk in terms of frequency or period. I want to pause for a moment and speak about that. If something has a low frequency, say that, versus high frequency, higher frequency, lower frequency. A high frequency has a short period, short amount of time. In this case, cycle, revolution. A slow spin takes a long time. Low frequency, high period, long time. High frequency, short period, inverse. The units tell you that, the concepts tell you that. Spend time getting this. This is critical as you go on. And then finally, we can go over here to acceleration. Now, the truth is we often don't analyze this here. So I'm just going to say, could use df dt, the rate at which that rate changes, but we usually don't. Not to say you can't, sometimes you can't. Usually we'll work in terms of angles. And so when we do angles, but of course the factor would still be 2 pi because the only thing we're changing is, again, revs to radians and radians to rev by that 2 pi factor. So how do we do it? Well, good old kinematics. It's just the same as before. We're going to see this. Omega changing. Well, that would be angular acceleration, alpha. Again, that's alpha. In radians per second, radians per second squared. Alpha average would be the change in omega over change in time. Alpha instant would be d omega dt. It's just like good old-fashioned kinematics in linear form. And it's all cool. What we want to do is see how this connects to the tangential motion and how this can be written in the case of, say, constant acceleration or otherwise. So we'll do that in the next video. Once I, let me see, make a comment here. I was going to say something. There's a subtlety that we're going to get to later, so let's not do that now. I can change the rate at which something rotates by, I can increase the rate of rotation, increase omega, or I could decrease omega, right? This is great. You have lots of homework problems where fans are speeding up and fans are slowing down. But you can also do this. And if you've ridden a bicycle or a motorcycle and you try to turn the direction of rotation, you'll feel it kind of fight you a little bit. It's an interesting thing. We'll get to that, and we'll have to use a little clever vector notation for that. So here I'm just talking about cases where I'm increasing omega or decreasing omega. Nice and straightforward as a starter. Are we good? So that's that. And let's stop that and do another video.